Hey guys, Mr. T here with the last video for this topic, hopefully. This one is on non-square matrices. So far we've only been dealing with matrices that have the same number of rows and columns, meaning they're square in shape. Obviously matrices do not need to be square. Some may have more columns than rows, others may have more rows and columns, so they could be rectangular. The Hungarian algorithm only works on square matrices, so we need a way to deal with non-square matrices. Thankfully, like maximization, all that's required to do is one extra step on top of the Hungarian algorithm, and this step is to add dummy rows or dummy columns, according to what we need, full of zeros to any non-square matrix to make it square. Then you apply the Hungarian algorithm as normal to find optimal assignments according to your objective. So let's try that out. We're hammering this swim team example, but this time we've got another swimmer, E. So the 100-meter times in seconds for swimmers A, B, C, D, and now E in backstroke, breaststroke, butterfly, and freestyle are shown in the matrix below. Find the optimal assignment of strokes to swimmers to minimize their overall time. So you may remember from previous videos, we used to just have A, B, C, D swimmers and backstroke, breaststroke, butterfly, and freestyle only. So it was a square matrix like this, 4 by 4. Now we have 5 rows by 4 columns. It is not square, so we need to apply an extra step of adding dummy rows or columns, in this case adding an extra column so that we have 5 columns and 5 rows to make the matrix square. Then we apply the Hungarian algorithm. So let's apply that first step. Redraw this matrix, but it's going to be square this time. And decide right now we need to add an extra column. So it's going to be 56, 59, 52, 53, and 0. We're adding a dummy column of only zeros. So 5 zeros going down. The rest of the matrix remains the same. 62, 67, 59, 49, 55, 64, 58, 51, 58, 60, 54, 48, 61, 58, 53, 50. We've added the dummy column or the dummy row, dummy column in this case. We've made the matrix square. Now apply the Hungarian algorithm. Step 1. We need to subtract the smallest value in each column, each row from the elements. So minus 0, minus 0, minus 0. 0 is the smallest in each row. Nothing happens in step 1, so it remains the same. Step 2, so to save me having to draw another one, step 2 is the columns this time, but because we did a dummy column, doing the step 2 of the Hungarian algorithm will actually cause some changes. The smallest value in column 1 is 55, so minus 55 from these. Smallest in column 2 is 58, so minus 58. Smallest in column 3 is 52, so minus that. Smallest in column 4 is 48, so minus that, and minus 0 from column 5. So now I'm going to redraw the matrix because I didn't have to do anything for step 1. I will have to do something for step 2. (56) take 55, 1, 62, 55, 67, 59, 61, 67, 55 take 55, 0, 58 take 55, 3, 61, 61 take 55 is 6, 59 take 58 is 1, 67 take 58, 59, 60, 61, 62, 67, 9, 64, 58, 59, 61, 62, 64, 60 take 58, 2, 58 take 58, 0, 52 take 52, 0, 59 take 52, 7, 58 take 52, 6, 54 take 52, 2, 53 take 52, 1. 53 take 48, 5. 49 take 48, 1. 51 take 48, 3. 50 take 48, 2. Oh, I skipped one. 51 take 48 is 3. 48 take 48 is 0. 50 take 48 is 2. And the last column remains the same. So step 2 has been done. Sorry about the brother and the missus. They are playing a video game. So step 3, draw lines to cover zeros. So look for the lines, the rows and columns with the most zeros. So straight away I'm going to draw that one. Next we have 2 along here, 2 along here, 2 along there, 2 along there. So how many lines did I draw? 1, 2, 3, 4, 5 lines. There are 5 rows in the matrix, so no need for step 4. 5 lines drawn, 5 rows in matrix. So skip to step 5, no need for step 4. Find a pattern of zeros. Pattern of zeros. 1 in each row column. So I need to find a combination of zeros, a pattern of zeros that is not going to override the number of zeros in a row and column. This one is by itself in a column, so I can choose that straight away. This one is by itself in a column, I can choose that straight away. This one is by itself in a column, choose that right away. This one by itself in a column, choose that right away. And then the only other zero that I can choose is this zero in a row and a column by itself. So that means that our optimal assignment is in that pattern on the original matrix. C for the backstroke, E for breaststroke, A for butterfly, D for freestyle, and here B was in the dummy column. It gets nothing. So therefore, optimal assignment and everyone's being noisy while I'm doing a video. Optimal assignment is A butterfly, B doesn't swim. He's the loser one. Doesn't swim at all. Too slow. C backstroke. D freestyle. E breaststroke. To minimize time. To minimize swim time. In other words, fastest team. Okay, so that is how you deal with non-square matrices. We've had 3 videos in a row with just doing the Hungarian algorithm. We can deal with different situations by applying one extra step to prepare for the Hungarian algorithm, but really the whole thing that you need to be able to do is the 5 steps of the Hungarian algorithm. Get familiar with them and you should be fine. So hopefully that helps you out with this, and I'll see you in whatever the next video is.